Hi everyone, my name is Manuel Rigger. I'm a postdoc at ETH Zurich in Switzerland, and in this talk I'm going to present query partitioning, which is a general and effective approach that we devised to automatically test database management systems in order to find logic bugs. In our work, we tested the database management systems, or DBMSs, shown on this slide. And just to pick a few examples, MySQL, many of which you probably know, is the most popular open source DBMS. Then TiDB and CockroachDB are highly popular as well. They're commercially developed by two companies and are prime examples of so-called NewSQL DBMSs. And as a final example, DuckDB is an emerging embedded database management system that is specifically geared towards efficiently executing analytical query workloads. Overall, it is crucial that these and other DBMSs work correctly, because even a single bug might affect many users in practice. In our work, we found and reported close to 200 unique, previously unknown bugs in the systems, many of which have already been fixed. In our work, we specifically aimed to find logic bugs, which are bugs for which the DBMS returns an incorrect result set. We believe that finding such bugs is important and also difficult, given the scope of today's databases, and also because, for example, unlike crash bugs, where it's immediately clear that a system is affected by a bug when it's triggered, this is not the case for logic bugs, where silently an incorrect result is computed. To give you one concrete example of a logic bug, I want you to consider this test case here that was automatically generated by our tool and exposed a bug in MySQL. You can see here that we have two tables, T0 and T1, each of which holds a single row with a single value, namely 0 and -0. And the query asks the DBMS to fetch the cross product of all rows from T0 and T1, where this predicate T0 C0 equals to T1 C0 holds. Now, what's the expected output? This is actually not immediately clear. It needs some domain knowledge, but MySQL in this case is expected to fetch the row, since this comparison should evaluate to true. When we tested the latest version of MySQL, actually MySQL failed to fetch this row. We reported this bug to the DBMS developers, who confirmed and fixed it, and now MySQL processes this query correctly. So the challenge in this line of work is to find a test oracle which can automatically validate the result set. So for example, for this test case, the test oracle would say that the result is incorrect. Now, some of you are probably considering already to use differential testing in this domain. Differential testing as applied to DBMSs would work like this. We would generate a test case that we would send to multiple DBMSs, for example, MySQL, TiDB, and SQLite, each of which would then return a result set. And then we could check whether all the result sets are the same. If not, then we have likely found a bug in one of the systems. Now, unfortunately, we found that the SQL dialects differ widely in practice. So the common SQL core is rather small, and DBMSs typically provide a number of extensions or differ and they do not strictly adhere to the standard. This observation is also confirmed by industry. So for example, Cockroach Labs, they stated that they are unable to use Postgres as an oracle when using differential testing, because it has slightly different semantics. So generating queries that execute yielding the same result on both systems is tricky. Now, in order to tackle this important problem of finding logic bugs in DBMSs, we came up with a novel test oracle. And the core idea is that we wanted to partition a given query into multiple partitioning queries, each of which computes a part of the result, which can then be combined to compute the original query's result set, which can then be checked. So if any discrepancies occur, then a bug in the DBMS has been detected. So here, more concretely, we would have a query generator that generates a query Q, to which we refer as the original query. You can also see here that we denote this or use this circle to denote the query's result set. Then based on the query, we would partition the result set combine the individual parts to a new result set, and the assumption is that these two result sets are the same. If they are, everything seems to work correctly. If not, we have found a bug in the system. Now, these queries that we derive from the original query are called the partitioning queries, each of which computes a so-called partition. And we use this diamond, this composition operator, to compose these individual partitions to yield this result set. Now, I guess while the general idea sounds plausible to you, it actually doesn't provide us with a concrete test oracle that we can use in practice. So we still need to find a valid partitioning strategy that stresses the DBMS in various ways in order to expose bugs. And there we had the following insight. Consider that we have a predicate phi and a row r. Then exactly one of the following must hold. Phi evaluates to true, not phi evaluates to true, meaning that phi evaluates to false, or phi is null evaluates to true, meaning that phi evaluates to null, given that SQL is based on or uses a ternary Boolean logic. Now, based on this insight, we can partition a given result set by selecting records where phi holds, where not phi holds, and where phi is null holds. We refer to these three predicates as the ternary predicate variants. Now, how did we use this insight to detect the bug in the motivating example? First, we constructed a simple original query. This query is not expected to expose any bug. It simply fetches the cross product of all records from T0 and T1. And indeed, MySQL fetched the correct result. And from this, we derived more complex partitioning queries. You can see here that we have a predicate which corresponds to our phi. And we have the non-negated, the negated, and the is null version of it. Now, for this query, MySQL unexpectedly returned an empty result set. Since the two result sets were expected to be the same, we could find and report this bug. So basically what we did is we took the general idea of query partitioning and instantiated it with the more concrete idea of ternary logic partitioning, or short TLP. So for this queue, for the original query, we had the simple query that fetches the cross product of all records from T0 and T1. And for the partitioning queries, we had the more complex queries with the non-negated version, the negated version, and the is null version of the ternary predicate variants. And for the composition operator, we used union all, which combines the records without filtering out duplicate rows. So this idea is actually applicable to testing a number of different features. I just showed you an example how we test work clauses here. It's a more structured approach of this approach. Namely, in the first column, you can see the format of the original query. In the second column, you can see the format of the partitioning queries, which is instantiated with the three times with the ternary predicate variants. And the third column shows the implementation of the composition operator. So this symbol here denotes the multi-set addition, which basically corresponds to union all in SQL. Now, I just want to provide you a second example to show you how the idea can be used to test aggregate functions. And first, I want to consider self-decomposable aggregate functions. I do not want to provide a definition. I just want to explain this on a concrete example, namely computing the maximum value over a set of values. Here, the composition operator is interesting because a partition in this context corresponds to an intermediate result rather than a subset of the result set. So each partition holds the maximum value that has been computed so far. And in the implementation of the composition operator, we need to use one additional invocation of the max aggregate function to compute the overall maximum value. To show this on a concrete example, I want you to consider this test case that triggered a bug in CockroachDB. So we sent the simple original query to CockroachDB, and CockroachDB here fetched null. And then we derived the partitioning queries, and you can see here that we have invocation to the max aggregate function within each partitioning query, and then one outer one that computes the overall maximum value. For this query, CockroachDB returned a single row with the value 0, and since the two result sets differed, we could find and report this bug. Now, besides self-decomposable aggregate functions, also a more general category of aggregate functions exists, namely decomposable ones. And again, I think it gets clear on an example. Namely, if you consider the average aggregate function, then it's clear that a single value to represent a partition is insufficient, because then we cannot compute the overall average value. So here we need to compute both the sum and the count, which allows us to then compute the overall average. We implemented our approach in SQLAnswer, which is a tool that is publicly available on GitHub. We implemented this tool as part of prior research, and it also went through the OOPSLA artifactorization process. SQLAnswer operates in 3 phases. It first generates a database, then a query, and then it validates the query's result. For the first 2 phases, we basically implemented additional database and query generators to support DuckDB, H2, and TiDB, 3 DBMSs that were not yet supported by SQLAnswer. And we also implemented test oracles for the DBMSs that we tested. Overall, we tested 7 widely used DBMSs. In 6 of those, we found bugs. And as initially mentioned, we found close to 200 unique, previously unknown bugs, many of which have already been fixed. Now, in terms of oracles, we found that the Were oracle was the most effective oracle, despite it being the most simplest one. The other test oracles found interesting bugs, but fewer overall. But one reason is actually also that we could only apply these additional oracles after the TLB Were oracle could not find any additional bugs. The reason being that they can also find some bugs that the Were test oracle can find, but they generate more complex test cases, so it's preferable to first find all the bugs using the TLB Were oracle. So we received quite a lot of positive feedback for this work. So the DuckDB developers, for example, mentioned that our testing efforts were very helpful for them, because if we wouldn't report these bugs, they would be slowly found by the users over the year. The approach also has been widely adopted in practice. To name a few examples, DuckDB now runs SQLAnswer plus TLB on every pull request as part of its continuous integration process. Ilya from Yandex contributed a TLB implementation to SQLAnswer to test their DBMS ClickHouse. MongoDB recently published a blog post stating that they adapted SQLAnswer to identify over 100 potential problems in their DBMS. PingCap ported the tool to a Go implementation and also support TLB in it. And finally, Cytos Data worked on an implementation of TLB that they contributed to SQLAnswer. And at this point, I also want to point out the excellent blog post that Natsli wrote. So she was the intern working on this, and she wrote a very understandable blog post on TLB and her experiences on implementing it in SQLAnswer for Cytos. And with that, I want to summarize my talk. So I presented that in our work, we aimed to find logic bugs in DBMSs. We came up with query partitioning as a general concept, and then proposed ternary logic partitioning, or short TLP, as a concrete partitioning strategy. Our relation has demonstrated the approach is highly effective and also general, since we found close to 200 bugs in widely used DBMSs. With that, thanks for listening, and I would be happy and glad to answer any questions that you might have. Thank you.